We should get started. You may remember that we were talking about psychophysics, which was a attempt to go from physical dimensions in energy units to psychological dimensions in unknown units. Part of the problem, of course, is trying to figure out what those units should be, because psychology doesn't really seem to come with its own units. Your impressions of things don't seem to come in their own units. So a lot of what psychophysics was about was trying to make that mapping. We had started off by talking about three different types of ways to make that mapping. One is about changing physical stimulus energies, and then saying, can you detect that in a threshold kind of way? How much do you need to know that there's now light in the room? There's now sound being produced. There's now something touching your skin, however lightly. Okay? We talked about that as detection, and noted that the theory was that there would be an absolute threshold. Theoretically, what an absolute threshold would look like is as intensity is increased, suddenly at some point, a critical point, if that means anything to you, there would be a shift from no awareness of those energies, and there would be stimulus energy here, right? But just below threshold, so you're not aware of it, and then a sudden jump to awareness because you crossed the threshold of sensitivity. Now the neurons are firing. Neurons, as we've already said, are 0, 1, right? They either are off or they're on. And so this made some sense theoretically, right? So this is kind of the theoretical model. What actually happens is that we get more of a sigmoidal curve where we again have no awareness, no detection of the signal. And then we have this period here during which, period by period, I mean range of intensity, during which there's some probability of detection. And then at some point, detection is like 100%. So far, so good? Easy, right? So the problem theoretically for them was that this is what they were expecting based on, let's say, kind of theoretical assumptions about how neurons work. And this is what they observed. So these two things are pretty different. And you could say, and what they did say, was that, well, probably what's happening here is that there's some differences amongst the neurons. And some neurons are tuned a little bit differently than others. Each one has its absolute threshold. Collectively, right, it takes more than one neuron to say, hey, something's here. So collectively, what you get is kind of an averaging of zeros and ones, if you will, ons and offs. And that gives us this form, okay? And so they're reasonably happy with this. And when they try to estimate what the threshold is, they go through the statistical procedure where they say, well, let's just say that above 50% is detection and below 50% probability of detection, okay, is non-detection. And we'll just drop a line down here and we'll use this as the threshold. Okay. So you may have read in your book, thank you for pointing it out, that in a book calls this procedure equivalent to absolute threshold. Okay. It is so not equivalent to absolute threshold. This would be evidence of absolute threshold over here. This is what it would look like. This is consistent with absolute threshold if there's a mixing of absolute thresholds, sure. But it's also consistent with any other process that probabilistically goes from 0 to 1. So it's not evidence for it, it's consistent with it, right? Which sounds kind of similar, but is not at all the same thing. So one of your classmates very kindly brought up that the book says that this is how it's absolute threshold, and that is totally not true. And I was so surprised to read it because it's like in physics, if somebody said, well, heat and temperature, they're approximately the same thing, right? Somebody in physics would go like, whoa, what are you talking about? Heat and temperature are nowhere near the same thing. They're kind of similar. They're related to each other, but they're not the same thing. Okay, so the book is just flat out wrong there. Probably that chapter was written by somebody who doesn't do perception work. So this distinction is worth making. Again, the distinction is between the theoretical absolute threshold idea and the actual measurement of a threshold, but not an absolute threshold. Okay. Questions on that? Sorry about the book being wrong. It's just cover that much ground, you're guaranteed to be wrong once in a while. Okay, so this is attempts at getting at threshold. Now we've done this. They've done this out the wazoo. They've done it and they've done it and they've done it. People made careers out of it. It's frankly a little bit hard to get too excited about. But let me tell you a little bit about your sensitivities. So this is pretty old, but it's a kind of a standard reference, and this is where this is coming from. So what's nice about this is that it's you know, we can think about things in these physical units, but this does a nice job of mapping it into real world things. So your system is so sensitive in terms of the detection of light, whether the light is present or absent, that it's able to detect a single candle at 30 miles away, which is 10 billionth of a watt. Okay, so unbelievable sensitivity. Really, really great. Now it varies, and I'm not going to get into all these complications, but it actually varies in terms of where in the color spectrum you are, and so on and so forth. Right? So people have done that too. But I won't bore you with it again. But you have a wonderful visual system. It works remarkably well relative to other creatures. And one of the things that people in this domain do is they tend to compare us with other species. Your auditory system is also really, really good. So you can hear, again, trying to put it into some everyday terms, a watch ticking, right? Back when we used to have watch, I guess we still have watches that tick, right? Watches that tick at 20 feet. And this is close to the amount of sensitivity you need to hear the blood moving through your own ears, which would not be good. So it's like the system is tuned to be as sensitive as it can be without hearing your own circulatory processes. Yeah, a downward, if you could hear that well. Right, so your auditory system is also really, really good. Of course, again, this depends on where it is in the frequency spectrum. Before you relate to that. Your sense of smell, not very well studied. So if you wanted to want to get into psychology and make your name, you could be the smell person. You might want to be careful with how you market that. But not that no one has done it, but compared to the auditory system and the visual system, the olfactory system, hardly touched at all. So this is a little bit romantic. A drop of perfume in a 6-room apartment, single drop you can smell. Right? And that, of course, has a physical measurement, which is in parts per million. Your sense of touch is also quite amazing. So a bee wing, very, very fine, tiny little thing, right, falling on your cheek from 3 inches away is enough for you to feel. And it depends on, obviously, where on your body, obviously, right? So your cheek is super sensitive, right? Your back, you get that whole bee on your back. Might not even feel it, but you also have a very nicely tuned sense of touch. Your sense of taste is also pretty good. So you can detect 1 teaspoon of sugar
dissolved into 2 gallons of water is a way to think about it. So some of these systems are like right at the top of the animal kingdom. Others, not quite so much. Like, you know, you got nothing, your olfactory system has nothing on a dog. Dogs are have crazy olfactory systems. But your visual system is better than theirs in some regards. So yeah, one of the things that people like to do is compare things across species. Because otherwise, like, well, how do you know how good you are? Just, it is what it is. So these are some of the thresholds for various domains. So that's all we're going to say about threshold itself. Next, we're going to go to differences, or what we might think about change in stimulation. Okay? Hopefully those, you can see why those are the same. It also has the name threshold in it, but don't be confused. This is really the difference part, okay? The change part. They talk about them as difference thresholds, but what we're doing is presenting you with some stimulus and then asking, given that stimulus is present, how much more or less do you need to say, oh, that something's different? Okay, that's why we call it difference or change. Okay, so again, this is the lowest level of physical stimulation. Again, we're in physical units necessary so that you can detect a change in that physical stimulus. These are going to be in units. Psychology was so happy to have some units that they gave them a jaunty little name, just noticeable difference. No, I'm not kidding. That's really is their name. They're in JNDs, just noticeable difference. So if you go to a party of experimental psychologists, people will make party jokes with JND as part of the thing, and you know all the people who are not in experimental psychology, what are you talking about? The JND means just noticeable difference. So that would be below the JND. That is below a difference that you can notice. Okay. And that's why there aren't a lot of people at those parties. But anyway, so just noticeable difference is a unit, and I'll try to explain what exactly I mean. It turns out you can quantify this quite precisely. Okay, so here is a old-timey schematic of this setup here. The kind of task you might do. So you could have 2 objects. I have to do it on the back. So these are yours. Come up afterwards. Not my props. They're here. We'll use them. All right. So you would be the subject. You'd be blindfolded usually in this sort of thing, so that vision doesn't contribute. I put this in one hand. I put this in the other hand. Right? And I say, are they the same or are they different? And that's the general procedure. Oftentimes, you'll start with one as the standard. This is just a matter of convenience. You'll see it also kind of play into the formalism that we're going to talk about. So that's why I bring it up. So let's say this one is the standard. Okay, so this is my standard. Now you hand me this one, and I do the same different. Okay. Simple. I think this one's heavier. I'm not sure. Very close to the JND. So that's how it's done. So in this example, I have 100 grams in my right hand. I'm sorry, 101 grams in my right hand and 100 grams in my left hand. Okay, so a 1 gram difference. What happened? Okay, so that is a so that is a possibility, right? And that is very close to the JND, but just underneath it. Now I do it again, and if you've noticed, it's now 102 grams versus 100 grams, and that is just over the JND, just over the just noticeable difference. Okay, so that, if that were the situation, now I would say, oh, they're different. Right, generally how this rolls. That's the procedure. And so you might have a ramp of these things. You might do it right where you go 98, 99, 100, 102, right? Go up that way, or you might just do it at random ways to perform the procedure, holding that standard constant. And then once in a while, you change the standard, right? So not very sophisticated experimentation, but simple. So you can do it with weights like this, right? Obviously, that's your kind of your kinesthetic sense. You can do a similar thing in the visual domain. So this is for saturation, let's say. So the standard here, which we're going to call I1, is, or intensity 1, is 100% saturated. Okay? It could not be a darker image. All the pixels are as black as can be produced by this projector, which it turns out is not very black, unfortunately. So I changed this a little bit because I have depending on the resolution of the screen, it works great at home, and then you bring it in here, and you're like, oh, it'll look exactly the same. So let's see how this goes. So now over here, we're going to have different second intensities, just like we have the standard here and different second intensities. So the question is, are those the same? Decide for yourself, are they the same? Okay, now another one, and again, I'm asking you to compare the successive I2s on this side to this I1. Yeah, this projector is not making those any different, for me at least. Now they could be a little bit different physically, right? So if I had a meter, right, that said how much reflectance is coming off of those, it might say, yeah, those are different, right? But visually for us, right, and this is part of the point of psychophysics, visually for us, at least for me, those aren't different, right? So now we're asking, is this one different from I1? I think it is for me. If we go again, okay, so now it's becoming clear. Now it clearly has crossed the threshold for me. Right, and so on and so forth. You might keep doing this, right? So, and at some point, if somebody isn't seeing it, you'd be like, whoa, hold on now. Either you're not doing the task that I'm trying to think of, or you need some help, right? Like you're really not seeing distinctions other people are seeing. So, right, so that's kind of how it goes. And that what they're looking for is the threshold for a particular domain. So on the left-hand side with the weights, the kinesthetic domain. The right side, the visual saturation domain. Obviously, the visual system has lots of dimensions that it could be interested in too, right? So you could do all the different colors, all sorts of things. Okay, but this simple saturation, right? So that's how it goes. Okay, so what we're trying to do is discover this threshold, and we call this difference the just noticeable difference rather than a threshold. We'll see in a minute why that is. So it turns out that when you do this, you get this really bizarre result initially that nobody could make any sense out of. Okay? And the result is this. The amount of stimulation change you need wasn't constant. Okay, so what do I mean by that? So let's do the simple kinesthetic version. Okay, so let's say I discover with my 100-gram weights that 2 grams was what I needed for you to detect. Everything over 2 grams, you got got really, really well. Everything below 2 grams, you pretty much couldn't detect. All right, so I have 2 grams. Right now, I change the value of that initial one from 100 grams to say 50 grams. Now, I do the same experiment. I'm expecting to need a 2-gram difference. Well, it turns out I need less of a difference. And if I make that weight even lighter, say 1 gram, I need like any little difference. Nowhere near 2 grams. That's weird. All right, so you might have thought that, well, it takes 2 grams from the initial experiment. It takes 2 grams to detect that kind of change. Well, it turns out it's a factor of initial stimulus, how much additional stimulation you need. Crazy stuff, right? But that's how it works. That's biology for you. Go figure. So this is a simple mathematical way to say that. It's called Weber's law. And it reads, thusly. So the smallest detectable change or difference in magnitude of a stimulus, right, the J and D, is proportional to the magnitude of the standard stimulus. Okay, so what he found is that it's not just always smaller or larger, but it's actually proportional to the magnitude of the stimulus that you're using as I1, as the standard. All right, so as I change my standard weight from 100 grams to 50 to 1, the J and D changes as a constant proportion of it. Okay? And that's what this is saying, because the delta I, right, is the change in stimulus intensity, right, as a proportion of the original intensity, the standard intensity, what we were calling I1. Okay, and that constant is the same for different domains, and it holds pretty well across like within that domain. So for kinesthetic sense, there's a particular factor, which is called a Weber fraction, that is K. For light sensitivity, there's a different Weber fraction K. For auditory stimulation, there's another one, right? So it's not just one. That would have been really cool, right? That would have been like, whoo, we saw something. It's local. It's like, it's within that sensory system. Okay, so that is what they mean by J and D, and it's now gives us the J and D, but it tells us the factor K tells us how to get to J and D, I should say. Right, so the J and D is always the proportion of the original standard magnitude. Okay, so another way to state this is that the greater the standard, the greater I1, the larger the change necessary to detect the difference. So lower J and Ds give us higher perceptual sensitivity. Higher J and Ds correspond to poorer perceptual sensitivity, obviously. All right, and this lets us kind of compare the sensory modalities to some extent. Questions on all that? All right, let me give you some examples of Weber fractions, which again are just statements of, for that modality, how much change relative to the standard you need, what proportion of that physical intensity do you need in that domain to detect a change. So these are ordered from most sensitive to least sensitive. Your visual system is really, really good. Right? So to detect a change in light, you only need 1/60th of change from the original stimulus. Your kinesthetic system is also pretty good. Right? You need 1/50th of change in weight. To name something, right? In order to detect a change. Your taste system, surprisingly, is really not that great. 1/3 of a change in parts per million, probably. Okay, so let me harken back to our original kinesthetic example, because it is literally concrete. So if our standard weight is 100 grams, And our comparison weight is 101 grams, as our first example was. Right, now we're going to incorporate in the Weber fraction. But we know that the Weber fraction is 1/50th. So we know that we need 2 grams difference here in order to change, because we've done the research in the past, right? So we know that this is going to be the J and D, 2 grams for this problem. Okay. So you multiply the current standard by the Weber fraction, gives you the just noticeable difference for this particular stimulus. Particular standard, I should say, standard stimulus. Super simple, right? But also perhaps can invite confusion. So if you have a question, I shouldn't say simple, because then people don't want to ask questions. But do you have questions? Does that make sense? The psychologists were very excited about this because it looked like there was a nice way to map physical quantities to psychological quantities. Right? Without too much commitment to other stuff, right? Difference, not difference. That's an easy one. Right? I don't have to get too excited about the vagaries of how much, how great is it? I don't know, man. How great is it? I'm like, give me a scale. Really hard. But if I can say different, not different, different, same, feels a little bit more like the solid ground. So they like this stuff. They like this stuff. Still stalling, waiting for a question, but question, I'll just go on. Right. All right, so this was one way to approach this, and people did like it, but not everybody. You know, you get a good thing, and next thing somebody comes along, they want to improve it. So this fellow, his name is S.S. Stevens, very famous psychologist, said, yeah, you know what? I'm just going to go for it. I'm going to take a shot at that scaling thing that you didn't like so much. I'm just going to do it. So I'm going to ask people, not same or different. I'm going to ask them how much. How great is it? How much does it hurt? How salty does it taste? How heavy is it? Okay. A can of worms that you can't even imagine. I mean, it's a barrel of freaking worms. But he was famous and he did this, invented some things along the way, so people still like it. So he proposed this thing called Stevens power law, where the relationship between stimulus magnitude, I is still serving in its same role as previously, okay, stimulus intensity magnitude, and subjective psychological experience, which we're now calling S. Okay? So on the right side of the equation is physics. On the left side of the equation is the outcome, as is often that, and is psychological stuff. Okay? So the K here is not the same K as previous. Okay, so point that K away. This is a new K, this is a new constant. All the action here, and if you're a math person, you already know, is going to be in that next column. The K is just a, doesn't look too great. K can be more or less that one. But the B is where it's at. So what he had people do is this thing called magnitude estimation, which is a somewhat fancy way of saying rate how intense something is. He gives them, there are a bunch of ways to do it, but for our purposes, let's just say, he says, I want you to rate the brightness of this, or I want you to rate the saltiness of this, or whatever. Here's something that I want you to use as to establish a baseline measure. I want you to assign this 100. So here's a pretzel. The pretzel is 100, okay, for saltiness. Now I'm going to give you, put some other things on your tongue, and you're going to rate their saltiness or whatever, okay, relative to the 100. Okay, so if it's less salty, down the scale, more salty, up the scale, right? You can kind of see that, wow, well, how do you know what the interval size is? Anyway, you're just supposed to do that. So that's the idea. That's magnitude estimation. This law breaks down at the extremes, so that's not so unusual. But let me jump right to an example because I realize I'm talking in the abstract still, so maybe this will help us. So here's our standard. Again, this is just a saturation, a red saturation. Right? You can see the visual system is super handy for these things, particularly for a large screen, because we can all look at it at the same time. So here is our standard. That's 100. And now imagine that you're in a controlled environment and things are coming up on the screen. And your job is just to slide a scale from you start at 100, you can go up, you can go down, and it's been described to you that this is about the saturation of redness. This is 100. Maybe they even gave you the endpoints. Like here is 0 saturated white. Here is 100% saturated. They would probably use the 100 term again. And that would be the reddest possible red. Okay, so now out come our stimuli. So we'll call them T's. Okay, so T1, trial 1 is this, and you go, oh, that's more. That's 160. Then this one seems to be less, and you go 50. Sometimes you can view this the whole time, depends on how they're doing it. This one, oh, very much less, 25, a lot more, and so on and so forth. You get the idea. So those responses, all right, are graphed here as a function of their actual redness, their actual stimulus intensity, I. Okay, I. Not your judgments of them. Their actual, like you can take a degree to which there's red spectrum light in it. So it's an actual physical quantity. But of course, what we want is out here, these are S's. Well, you didn't label the axis. You should label the axis always. So this should be S. Okay? So these are your ratings. You're the subject. Now it doesn't always work out quite as neatly. But this particular B is 0.6. And there's a K here too that just determines how far up off the intercept point. And so this beautiful thing is the power law, right? And it's a power law in that it has this beautiful curvilinear shape. And so Stevens is saying, look, here's what happens in psychological systems, perceptual systems. You have a range over which you're super sensitive to changes. Okay? Really, really sensitive. And then beyond the this is again results in this kind of even differentially sensitive the different regions of the intensity spectrum. All right, so that's another, this is the third, right? So we did threshold, difference or change, and this is scaling. All right, I won't go on and on about scaling and discontenting. Questions on this? So power laws are fun to play with. And it does seem like most of those mappings have some power law like properties. So classically, it's thought to kind of be at this junction here, right? We've got physical events in the world, and we go from energy to sensation. So the idea is to understand and identify properties of energy and then how they get mapped into sensation. There we talk about these three different means that people have used to try to make that mapping. That only gets us to, has something happened in the world? Is there energy in the world in this modality? The bigger and thornier issues are going to be here, where we go from sensation, perception. So how do you go from sensation into knowing about objects and events and people and the other stuff of your regular daily world, right? And so that transition, it's really, really difficult. Let's see if I can do it. Okay, so now we're gonna. Am I still sharing? And I am good. So we're in sundry senses, and we're going to group the senses into types of sense. And the typology depends on what sort of energy they're converting. So the wave senses generally do their business to converting energy that is in wave-like form. All right, so the auditory system is a great example. Visual system, we can think about light as wave-like. It's convenient. And of course, there are other ways to think about light as well. So those are going to be our wave senses. It's not there. We're also going to have chemical senses. So senses which detect changes or presence of particular structures, chemical structures in some medium. So olfaction and gustation. We also have these skin senses, which we could have called perhaps mechanical senses, in that it's mechanical energy as it impacts the skin that is driving your kinesthetic sense. Right, so things like pressure, temperature, pain are all pressure, but it turns out that they work quite different. All right, so we're going to start with the wave senses. Fix that slide. Troughs. I should just get another thing here. Anyway, so this is supposed to be a sine wave. So if you know sine waves, you can be like, well, that's weird. But anyway, it'll do the job. So the idea here is that the waves of energy, whether they're auditory or in the visual spectrum, have some characteristics as waves, and they have general characteristics. And the measurement of those characteristics is how people in audition and vision measure the energies in that system. Okay, so that's why we're going to take this little excursion. So generally, when you have a wave, you can think about it as moving like a sine wave from some origin out in time. Okay. And it has amplitudes that go positive, negative, positive, negative, positive, negative. Okay, so the amplitudes is always the distance from the origin 0 to the top of the wave, the crest of the wave, the height of the wave, right? And it's also the same distance, because theoretically they have to be the same, as the negative. Okay, so sine waves are always going like that, right? And that this waveform description is very, very general and very well understood now. So for our purposes, we're going to think about amplitude and either wavelength or the two parameters described, right? Deviation from the origin, right? The maximal deviation from the origin. The frequencies are in cycles per some unit time. And usually it's like cycles per second. What's a cycle? Well, a cycle is how long it takes to go from the origin to the max to the min and back. That's a cycle. So when you have frequency, the question is how frequent is the cycle? Okay, perfectly fine way to do it. So we're putting things in terms of number of cycles completed per unit time. Again, usually cycles per second, which some people call hertz, abbreviated HZ. So all that may be familiar, may not be familiar. Don't know. Okay, so for our purposes, the amplitude, call it the height of the wave at the peak or the trough, they are equivalent, and it corresponds to the energy in the wave or its intensity. Okay. Energy in the wave or its intensity, which makes some sense. Right, so if you're at the beach, big waves, more energy, be careful. Small waves, less energy, not such a worry. The wavelength, right? I just did frequency. We can do wavelength too. Is the distance between the peaks. So that's another way to talk about how often things happen. Right? These things are thought to be completely regular. I guess I should say that part. Right? That's an assumption. They're thought to be completely regular in this sort of analysis. Okay. So the frequency is the number of cycles per unit time. Right. So the wavelength and the frequency both correspond in the psychological sense to things like quality and pitch, color, and that sort of thing. Just weird. When you think about sound, the amplitude corresponds to loudness. Frequency corresponds to pitch. When you think about the visual system, the amplitude corresponds to brightness, and the frequency okay, so this is just we're gonna talk about wavelength, we're gonna talk about frequency, and we're gonna talk about amplitude. So I'm just trying to make sure that those concepts have a little bit of grounding here. Questions on any of those concepts? Okay, so that's going to be the basis for the wave senses. We'll start with the auditory system and just a little bit of anatomical detail. The ear is one of those things where you go, how on earth did evolution come up with this? Because there are all these specialized pieces in there that you just can't imagine what their function was until there was an auditory system. And yet somehow here we have this thing, each with this thing like a chain of required mechanical interactions that must happen for you to hear. We're going to break the auditory system up into those that do what we're going to call transmission, and it's going to be transmission of the energy in its auditory form. Good enough. And then transduction, where transduction mechanical energy that so that's going to be the story. We can do we've got 1 minute. So we can do the collection part very easily. You have the so everybody not laughing at you or anything, but honestly, they are. We have the auditory canal, which you probably don't think of very much. Right? And that leads to this beginning of the transmission process, right, which is going to be the tympanic membrane or the eardrum. All right, so we'll return to the pin a little bit later down the road, but next time we'll go right into so